Welcome back to linear algebra. In this video, I want to talk about the orthogonal complement of a vector space. Let me get my head out of the way and put down the formal definition here, and then we'll spend some time dissecting it and trying to make sense of it. We need to start off with a vector space. So let's let W be a vector space and specifically a subset or a subspace of Rn. We say that a vector v in Rn is orthogonal to the vector space W if and only if v is orthogonal to every vector in W. And remember from previous video that orthogonal, sure, we have the idea of a right angle, but also the dot product is 0. And that idea is what I'm going to use here in this definition. The orthogonal complement of W is denoted as a W with an upside down T. You may have seen this upside down T used to mean orthogonal or perpendicular in other contexts. So we can read this as W perpendicular, or the orthogonal complement of W, which is a little bit more verbose, but not a lot. But it is all the vectors V such that V dot W is equal to 0 for all W, or for all vectors W in vector space big W. V dot W equals 0, remember, is what it means for V to be orthogonal to W. So the orthogonal complement of a vector space is the set of all vectors which are orthogonal to that vector space. And in 2 and 3 dimensions, this is really easy to understand, although it can be a little bit difficult to draw. A one-dimensional vector space is a line. A one-dimensional subspace of R2 is a line in the coordinate plane. A one-dimensional subspace of R3 is a line somewhere in space. A two-dimensional vector space is a plane. A two-dimensional subspace of R3 is a plane somewhere in three-dimensional space. I bring these up because a plane is perpendicular to a line. Or if you think about a line in space, every vector which is perpendicular to it could be in any rotation around that line, but sticking out at a 90-degree angle. And that limitation takes us down from three-dimensional space to a two-dimensional plane. So for example, let's consider the span of the vector 1, 0, 0 in R3. Right? So 1, 0, 0 is the unit vector in the x direction. And I guess I should name this. This is the span of this is what I'm using as W. All right, so 1, 0, 0 is a vector that goes in this direction. And every linear combination is any other vector that lies on the x-axis. You can get every vector on the x-axis, and you cannot get any vectors away from the x-axis. I claim to you that the orthogonal complement of this vector space is the span of the vectors in the y direction and in the z direction. All right, so that's all of the vectors in the two-dimensional plane, the YZ plane. Now, just claiming it isn't enough. Let's go and prove that that's the case. Right? So let's pick a vector W in our original vector space. And from the definition, the span of a single vector, W is a vector with components c, 0, 0 for some constant c. Now, if we pick a random v in R3, we know that v has components x, y, z. And if we take the dot product of v dot w, we will get c times x, 0 times y, 0 times z. In order for my vector v to be in the orthogonal complement of w, that means that v dot w must be equal to 0, which means that c times x is equal to 0. We can't control c. Remember, c was the constant in the linear combination that created that vector in the vector space. We need this to be true for every value of c. And the only way we can get this to be true for all c is if x is equal to 0. That means that my vector v must be 0, y, z. And if I split that out, this is y times 0, 1, 0 plus z times 0, 0, 1. It is a linear combination of the other two standard normal vectors, or the standard unit vectors in three-dimensional space. And the span of those vectors is the YZ plane. Right? A little bit backwards of how we usually talk about things, But I really wanted to lead this one from the geometric perspective and from the three-dimensional perspective, because thinking about complements when we get to higher dimensions is a little bit brain melting, right? If you have a three-dimensional subspace of a five-dimensional vector space, well, three-dimensional space is what we live in. The orthogonal complement is a plane perpendicular to that. How do you envision a plane perpendicular to three-dimensional space? I have no idea. I'm legitimately asking. If you have a way to do that, please do share. But in two dimensions, we can understand the orthogonal complement very readily. In three dimensions, it starts to get to be a little bit messy, but we can kind of make do. If we go to a four-dimensional vector space, understanding anything visual in four dimensions makes my brain want to turn to goo and ooze out my ears. So we start with this idea. When we say orthogonal, we literally mean it. The orthogonal complement of a vector space is the set of all vectors perpendicular to all of the vectors in that vector space. And that will be true no matter what kind of dimension of vector space you are looking at. Now it's time to get crunchy. Let's look at a pretty classic theorem. Let W be a subspace of Rn. Then the orthogonal complement of W is also a subspace of Rn. We kind of saw that in the example already, but let's dive in and see if that makes sense. In order to show that something is a vector subspace, there are two properties we need to establish. The zero vector has to be in the set. Well, zero dot with anything always gives you the zero vector. That's nothing new. The other thing we need to establish is that the orthogonal complement is closed under linear combinations. And that's a little bit more challenging, or at least a little bit more time consuming. Well, let's pick a V1 and a V2 in W complement and consider the linear combination C1 V1 plus C2 V2. Once again, in order to show that it is in the orthogonal complement, we need to pick a W in the vector subspace W. And then take the dot product of our linear combination with that W. Of course, dot products have the distributive property. This is C1 times V1 dot W plus C2 times V2 dot W. And since V1 is in the orthogonal complement, that means that V1 dot W is 0, and likewise V2 dot W is 0. And so the 0 vector is in the complement. Linear combinations are within the complement. Those are the two properties it takes. The orthogonal complement is itself a vector space. Let's take a look at one more theorem on this. Once again, we'll take a random subspace W, and this time I claim that the intersection between W and the orthogonal complement of W is the 0 vector. Right. Of course, since these are two vector spaces, we know that the 0 vector must be inside of each of them. So the singleton 0 is a subset of the intersection of W and its orthogonal complement, but we need to show that there is nothing else in there. So assume that we have an arbitrary vector v in the intersection. Well, being in the intersection means that you are in the vector space and you are in its orthogonal complement. And the definition of the orthogonal complement tells us that any vector in the orthogonal complement dotted with any vector in the vector space, like v and v, must be equal to 0. But from properties of vectors, the only vector which, or the only Euclidean vector which you can dot with itself and get 0 is the 0 vector. Right. So we knew that the 0 vector was an option. We've now shown that the 0 vector is the only option. Right. And to show two sets are equal to each other, you show subset inclusion in both directions, which we have just done. Vector space W intersected with its orthogonal complement is equal to the 0 space. I have a couple more theorems here. I'm not going to take the time to prove these because I only have so much time available. I claim that the orthogonal complement of the orthogonal complement of W is W. I think this one should make sense. If the orthogonal complement of W is all of the vectors perpendicular to W, well, then the orthogonal complement of that, all the vectors perpendicular to all the vectors that are perpendicular to the vectors in W, it makes sense that that's the vectors in W. Technically, there is some subtlety in that claim that I should go into in more detail, but I think that surface level understanding of why that's the case should suffice. We know that everything in W is perpendicular to everything in W complement, which means that the orthogonal complement, everything in the orthogonal complement, is perpendicular to everything in W. It's a cyclic relationship. It makes sense that it would bounce back to itself like this. The other thing I want to claim here, if you take the dimension of vector space W and the dimension of its orthogonal complement, together you get n, the dimension of the Euclidean vector space we started in. This one should make sense to you based on the example we did. The orthogonal complement of a line in three-dimensional space is a plane. The orthogonal complement of a plane in three-dimensional space is a line. A line is one-dimensional, a plane is two-dimensional, 1 plus 2 is 3. All right. So there's, again, it's an example, it's not a proof that holds in general, but I think it gives the general idea of what's happening here without us having to go into too much detail. The last thing I want to do is one of the big ideas of linear algebra. Some of the vector spaces that we have worked with previously fall into these definitions of orthogonal complement. Let A be any M by N matrix. With just that, the orthogonal complement of the row space of A is the null space of A. Remember what these things mean. If we define A as having rows, R1, R2, all the way down to Rn, and let's redraw that nicely centered. Then the row space of A is the span of those M row vectors, right? It's an M by N matrix. So we have M vectors in Rn. And remember also that the null space of A is the set of all vectors such that when you multiply A times that vector, you get the zero vector. But think about that a little bit more carefully. Pick some vector v in the null space of A. And think about what it means to multiply A times V. We've defined A as a bunch of row vectors And to calculate a product of a matrix with a vector, the new vector has components which are that row dotted with V. So we get row 1 dot with V. We get row 2 dot with V, all the way down to row M dot with V. But because I picked V from the null space of A, those things are all 0. So take any of the row vectors, dot it with V, and you will get the 0 vector every single time for a vector V in the null space. With all of that as background, I can pick an arbitrary vector W in the row space of A. And with that, I know that the row space is the linear combinations of the row vectors. So some C1 times R1 plus C2 times R2 all the way down to Cm times Rm. And if I take W and dot it with V, my vector from the null space, I can distribute. And this is going to be C1 times R1 dot with V plus C2 times R2 dot with V all the way down to Cm times Rm dot with V. And I just established all of those things are 0. So that means that every vector in the null space is in the orthogonal complement of the row space. I'm not going to walk through and show you that this works in the other direction. But if we assume that a vector is in the orthogonal complement, you kind of go backwards. You get this relationship offhand, which gives you that all of these things are equal to 0, which gives you that the vector is in the null space as well. Or I guess a more direct route that I didn't think of until I was talking through this. If V is in the orthogonal complement of the row space, then V dot each vector, each row vector must be 0 because each row vector is in the row space itself. And with just that, you can show that A times vector V is 0, so V is in the null space, and it works the same in the other direction. Something that I don't want to get into in any detail this semester is this proof can be combined with a very similar one, taking the column space of a matrix and the null space of the transpose of the matrix. Well, the column space of a matrix is just the row space of its transpose. And so it makes sense that the column space of the matrix is orthogonal to the null space of the transpose of the matrix just as well. For that reason, you will see the row space, the column space, the null space, and the null space of the transpose referred to as the four fundamental spaces of the matrix. We're not going to build on that in any way in this course, so I don't want to go into it in any depth, but it would be a significant omission if I didn't at least mention that somewhere. So we'll end the video with that and with a relatively simple problem for you to try based on this theorem. I want you to look at this matrix, 1, 1, 1, 1, 0, negative 1. Find a basis for the row space of the matrix, find a basis for the null space of the matrix, and then the key here, take each of the basis vectors for each of those two spaces and show that those basis vectors are orthogonal. Right? Multiple basis vectors within one space will not be orthogonal to each other, but every basis vector of one space will be orthogonal to every basis vector of the other space. And from there, you can generalize. I'm not going to necessarily ask you to generalize, but from there, you can generalize that every vector in the row space is orthogonal to every vector in the null space, thus verifying the theorem we just proved. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.